Okay, so geometry processing is my home community, right? So I started publishing in SGP, I think, more than 15 years ago. Okay, I think my first SGP paper is back in 2007. Okay, so very recently I've been publishing more in vision conferences. I do think there are a lot of synergies between geometry processing and 3D vision, which is arguably the hottest topic in computer vision right now. I think this tutorial essentially is basically some summary of some of the stuff I did and some relevant stuff that the community did. And I do believe that there are a lot of applications of geometry processing techniques, okay, in machine learning, 3D vision broadly defined, okay. Let me start, right? So we are in the foundation model era, right? So the scaling up is the key, right? So generative AI. If you look at the 3D community, that deals with generating learning 3D geometries, we have the serious issue in data, right? And if you look at what we use to train foundation models for ChatGPT, vision language models, they at the scale of trillions of tokens. But in the 3D domain, even for object words, we have at most 10 million 3D objects, right? So there's about 1 million in terms of scale, right? Between text and image data and the 3D data we have. In addition to that, we also have long tail distribution, meaning some of the categories that are well represented, like the chairs and furniture models. But in many other categories, we only have 10, right? 20 models, okay, many categories, because those categories, those models are very difficult to model by humans, right? So if we don't have sufficient data, then we won't be able to train foundation models, right? And if we don't have foundation models, then we will not have a lot of scalable applications, okay? And I do think, for example, ChatGPT, those large language models, they're widely used, deployed in industry now, right? Okay, so how to address the data issue, right? So there are two ways. One way is to use 2D data, right? For example, if you care about object level 3D data, right? So we can so we can use 2D product images, like the billions of product images, right? Each object has a few views, right? If we are able to, with construct 3D models, from those product images, we can potentially address the data issue, in particular for object level applications. So this is a very hot topic right now, and my group has been also working in this domain, right? This is something I want to talk about. It's less relevant to this community, but my argument is that data is not the only issue, right? Because you look at OpenAI Sora model, right? So many of you have seen this, right? So videos are very realistic, right? It will kill, will kill many jobs, right? In particular in movie industry, right? Certainly, those videos look very realistic. But if you look carefully, we have some issues, right? Right, so Sora models, right, those synthetic videos, they do not preserve simple geometric structures, line structures, like straight lines, vanishing points. So we do have those geometric structures in the training data, right? But then if we use generic neural network to do some interpolation among the training data, right? Conceptually, you can think about how synthetic videos are generated, right? They are interpretations of training data in some form, okay, using diffusion models, transformers, right? Certainly, those neural architecture, they do not model geometric structures, right? And the diffusion models do not model geometric structures. Then, even with training data at a smaller scale, right, only a few companies can afford, right, both in terms of the training data and in terms of amount of compute, right? You do some interpolation, right? We do not preserve geometric structures, right? Even with massive amount of data, right? So you can argue that, oh, the videos look very nice, right? That is one argument, right? Because our human perception system is insensitive to those, okay? Right? If you only care about whether the movies look nice or not, right? This probably is not that important, okay? But in the 3D domain, we care about a lot of geometric structures that are vital, okay? Vital, okay? For example, if you care about how to use those videos to do 3D reconstruction, then those line structures become very important, okay? You will not get very good 3D models from those synthetic videos, okay? Right, if perspective geometry is not strictly preserved. Okay, so my argument is that we do need to model 3D geometry, geometric structure, right, in 3D learning, right, if we care about those geometric structures for 3D applications. But unfortunately, what people have been doing in 3D learning, right, is something straightforward, in many cases naive, right? So first of all, if we want to do any deep learning in 3D, one very important problem to solve for any machine learning problems is how to represent 3D data in those standard forms like vectors, matrices, sets, and graphs. Because if you want to apply machine learning, you have to encode 3D data in those standard forms. So this is something I think very exciting research during the past decade, right? Pretty much for all those 3D representations that we have been studying in geometry processing, in graphics, we have at least one, sometimes a few, okay, well-known neural representations like deep SDF, point-net, right, mesh GPT, etc., right? And also for the purpose of 3D reconstruction generation, we have developed a new representation called triplane representation that connects the 3D domain, right, with 2D domain, right? So this was developed in the deep learning era, okay? So I think this is very exciting, okay? It's not completely solved, and in each year, if you go to CAP or CGraph, right, you'll see a few new representations. I do think those representations are quite valuable. But now if you look at generation from the machine learning perspective, right, so I would say that this becomes next exciting, right? So first of all, we have some breakthroughs in machine learning models, right? GAN, VAE, normalizing flows, and very recently diffusion models. So those models were developed in the image and video generation community, okay? Then what I think is because a little bit naive is that in the 3D domain, what people have been doing is that whenever we develop some machine learning models for image and video generation, then in the 3D domain we adopt, right? So we did this for GAN, for VAE, for normalizing flows, and very recently for diffusion models, right? So you can continue to do this, right? In fact, I don't think generative models, okay, right? We have the ultimate generative models, right? So this field is still being developed, right? Very recently we have those flow models, right? So we can continue to do this. Whenever we have new models come out, then in the 3D domain we adopt. In fact, state-of-the-art generative models, right? There are many startup companies in China, right? A few, right? So Tribal, right? Hunyuan, right? Those models, they adopt rectified flow, which was developed by my colleague at UT, right? So you can continue to do this. But then the argument is that, is this actually sufficient, right? So let's look at the difference between image and visual generation and 3D generation. Let's go back, right? So the purpose of image and video generation, right, is to generate images and videos that look nice, right? If that is the case, we have this very standard representation called patches, right? A grid-based representation. If you do distribution alignment very well, then we can generate very realistic-looking images and videos, okay? And this is the reason why diffusion models have been very, very successful, okay? But then in the 3D domain, we care about a lot of priors, okay, that are critical for many applications. And we do not talk about those priors attributes for image and video generation, right? So that is the difference. So what are those priors? So number one, right, if we generate a 3D model, right, if we are a graphics person, one very important application is manufacturing, right? You want to print the object, right? Then the model has to be physically stable, right? Otherwise, it will break during the manufacturing of 3D printing procedure, right? Physical priors are very important. And if you care about the robotics application, right, you generate a 3D environment to be interacted by agents or robots, right, doing some simulation, physical properties, right, are very important. But we do not model physical properties in image and video generation, right? So this is actually very important. And, right, in fact, if you use standard generative models to generate 3D shape, many shapes are not physically stable, right? In fact, many shapes have topological priors. What are topological priors, right? A shape has to be connected, right? If you use an implicit representation to generate 3D shape, many shapes are disconnected, right? If you are familiar with deep SDF, right? So this is, the topological priors are also very important, right? And what are other topological priors, right? Number of holes, right? Number of voids, those are topological priors, okay? Right, so we can also have deformation priors, right? Those are related to deformable objects. I will talk about this in detail, okay, in this tutorial, okay? Okay, and we can also have function priors, right? Shape, we generate the shape to be used by humans. Right. All right, maybe I just need to keep on pressing this, okay? Now, if we use the generic deep learning models and training objectives, very similar to the fact that solid models do not preserve straight line structures, right? You're not going to preserve those more advanced structures, okay? But they are very important, okay? So we do need to preserve those structures, okay, in generative models. So that is this tutorial is about, okay? So how to enforce those priors, okay? So there are two strategies, okay? One strategy is you're going to enforce those priors, right, when developing new networks. So if you are very interested in differential geometry processing, you'll find, I will talk about two papers. So you'll find those two papers to be very interesting, okay? I promise you, okay? I really like them. But they're very specific. We do not really have a framework to develop those machine learning models. It's case by case, okay? If we want to have a framework, then we need to develop regression losses, okay? We do have some frameworks behind this, okay? I will also talk about, okay, in the second and third part of this lecture, okay? Okay, let's begin with the network design, okay? I will talk about two papers, right? The first paper is about neural implicit representation that uses some very simple differential geometry concepts, okay? I think all of you should be aware of that, okay? The second paper is about how to enforce mappings in 3D are injective, okay, one-to-one mapping, right? And this is very important for deformable nerve, okay? I will talk about that, right? So let's begin with the first paper, right? As I mentioned, right, this is implicit representation and uses a very simple geometric concept, right? So what is the simple geometric concept, right? Is that if you have a shape where the boundary is a 2D surface, right? If we have 2D surface, then we have the notion called this canonical coordinate frame, right? Defined by the normal and principal directions, right? So in this coordinate frame, right, locally, the surface is quadratic, right? Quadratic surface, right? Defined by in this coordinate frame, right? Is a quadratic surface, right? And defined by the principal curvatures, okay? And in this coordinate frame, the sine distance function is also a quadratic function, okay? So that is a very simple geometric concept. Now, then you go back to this deep SDF, which widely used, right? But how many of you know this deep SDF? Okay, a few of you, right? So the idea here is that, so what is deep SDF, right? So for deep SDF, right, it's in a 3D domain. For any point, right, you want to feed this point into a feed-forward neural network, right? This is defined by MLP, right? It's multi-layer perception, right? So it's a multi-linear layer. In between, we have a loop, right? Then it predicts the sine distance function of this point. So essentially, the neural network, okay, encodes the sine distance function of the underlying shape, right? So if you have the sine distance function, then the zero-level set gives you the shape, right? So this is called implicit representation, right? Which is widely studied in geometry processing, right? So you can also extract the sine distance function from a point cloud, right? That was introduced in Hughes's Hobby's seminal paper, right, at SIGGRAPH back in 1992, okay? Right now, we use a neural network, right? Right? The network takes a point as input and then predicts its scientific function, okay? Value, okay? Then later, there's another paper called Deep LS, right? So it actually decomposes, right, the 3D volume into using a grid, right? You associate each cell with MLP, right? So when decoding SDF, you first locate, right, the point in a cell. Then you use MLP associated with that cell to decode its SDF, right? So the argument is that in each cell, the shape variation is a lot smaller than the entire shape, right? So if you do this, essentially you don't need a very complicated MLP. Otherwise, you have to learn the entire distribution of entire shape using a single MLP, right? If you localize, then the shape, then the MLP doesn't need to be very complicated, right? Okay, so that is the prior art, right? My argument is that if we want to do this locally, and we know that through the simple geometric insight locally, we just need a quadratic surface, right? Because the SDF is a quadratic function approximately, right? So that is a very simple geometric concept. If we are able to orient a shape locally, right? When decoding SDF, if we are able to transform the point properly, right? In the extreme case, right, by the normal and principal direction, right? Then we just need to learn a quadratic function, right? That is ideal, right? Quadratic function is a lot simpler than MLP, right? Of course, in reality, it becomes slightly more complicated, right? Okay, so that is ideal, okay? So by the way, this deep SDF, this machinery has been widely adopted, okay? So this is called periodic activation function. Those papers, right? This paper has 2,000 citations. And position encoding, right, which is another widely used strategy, right? Both papers do not model the notion of local coordinate frame, right? If we model that, you don't need a very complicated MLP, right? So this notion of coordinate frame is orthogonal to those recent developments, okay? Okay, so the key idea is that if we want to learn the local MLP, we also learn jointly the coordinate frame, right? So the idea here is that we have this cell, right, grid that discretizes the space, and we associate each cell with a learnable coordinate frame, right? And we learn the coordinate frame both during training and during inference. Then we also learn the MLP after factoring out the coordinate frame, okay? So that is the idea, okay? So this is actually very interesting, right? So if you are familiar with image-based CNN, right? So I jump back and forth between 2D and 3D domain, right? So if we work in image recognition, this is actually a well-known paper, okay? How many of you have seen this? Okay, a few of you, okay? What do you actually realize, right? You look at the low-level feature. What do you observe? What do you observe? Look at those filters, right? So you have a few patterns, but they are rotated, right? You have rotated copies of the same filter, right? So if you are able to factor out the rotation, then you can annotate those filters to encode other 2D patterns. If you do not factor out the rotations, then you have to allocate those filters to encode the rotated copies of the same edge detector, right? Then you want to argue why in the 2D domain people do not factor out the 2D rotations, right? Why? Because in 2D you actually don't know how those rotations should be, right? It's very complicated, right? But in the 3D domain, we have the knowledge of this normal and principal directions. We have very strong prior knowledge, okay, about the underlying rotation, right, coordinate frame, okay? And in fact, also developed, I think introduced the first version of this conference, right? You can actually feed a parabola or do PCA to estimate the normal and principal directions, right? Right. So that is a very strong prior knowledge, right? And in fact, that becomes very important, okay? And in the 3D domain, we do know how to initialize, right? Initialization is very important, okay? In the 2D domain, we don't know how to initialize, okay? That is the challenge, okay? Okay, right, so that is the idea, okay? During training, we optimize each cell shared MLP and the latent code of the local shape. And the coordinate field, right, is a rotation and translation, okay? Right, during training, we optimize this. During inference, we freeze the MLP, we optimize the latent code that characterize the shape locally and the coordinate field, right? During inference, we also need to optimize the rotation locally, okay? And we need to figure out a way how to initialize the coordinate field, right? So that is done by PCA, okay? Principal component analysis among the points locally, okay? The smallest principal direction gives the normal, right? The others approximate the principal directions. There's a paper that provides theoretical justification of that. As I mentioned, locally we have a quadratic surface, so we do need a quadratic layer, okay? And this is also important, okay? I will show some numbers, okay? So the result, we don't need a very complicated MLP to achieve the same result, right? Without factoring out the coordinate field. And with the same network capacity, we have reduced the generalization error by 52%. Right. So as I mentioned, right, initialization is very important, okay? If you use random initialization of coordinate frame, then you optimize the coordinate field, you get some improvement. That is the second row, right? But not a very significant improvement. If we start with PCA, then we get very big improvement, right? Because I mentioned, right, PCA gives us strong prior knowledge about the underlying direction, okay? The normal and principal directions, right? Then you do fine-tuning, we get a much improved result. So this is, I think, why in the 3D domain, we do need to enforce prior knowledge about the 3D data, okay? Right? And this table shows this is very important, okay? And we have very strong out-of-distribution generalization behavior and quadratic layer, okay? The same amount of parameters, if we make the loss layer to be a quadratic layer, we have better generalization error, okay? Okay, right, some visual result, right. So I also want to mention that the biggest population in 3D vision comes from the vision community, right? So I think they have limited knowledge about different geometry of surfaces, okay? To my surprise, I thought there's a very similar idea should have been developed, okay? Maybe 1 or 2 years after deep SDF, but this was published last year at NERPS, okay? Very recently, okay? So I do think that the 3D learning community can benefit a lot from you guys, okay? Right. Okay, so that is the first paper, and we are working on how to do 3D generation, okay, on top of this neural representation, right? That's still ongoing, okay? All right, then let me talk about second paper, okay, which is about how to enforce 3D mapping that is one-to-one, okay? This is used in the context of NERF, neural reference field, right? Which probably is the hottest topic in graphics right now, right? If you think about how many papers that we have in a subfield in graphics, right? I think NERF or Gaussian splitting, right? Those two topics, right? We have thousands of papers each year on those, right? So what is NERF, right? The background is that we do need to deform a neural field, right? That is injective, okay? So what is a neural field? In general, what is a NERF, right? So NERF is used for non-view synthesis, right? You reconstruct a new representation. Then you want to render this new representation for non-views, right? So standard way to do this is that you have multiple images, you reconstruct a textured 3D model, then you can render the textured 3D model for non-views, right? And very recently, there's a breakthrough, two breakthroughs, right? First breakthrough is called NERF. The second breakthrough is Gaussian splitting, which arguably is a generalization of NERF, but it has less training time and better quality, right? But this lines of research started with NERF. So NERF is very similar to deep SDF, right? So you have two implicit defined neural networks, right? That defines a density at each point and a color at each point in a viewing direction, right? Both are defined by MLP, right? If you have that, then you can do rendering using volume rendering, okay? Do some integral, okay? Right. And both color and density fields are learned from training images, also through neural rendering, okay? Right, you solve optimization procedure. NERF takes hours, minutes, and Gaussian splits takes less time, okay? Right. Okay. Right. Now, that is about static scenes, right? You have multiple images of a static scene. If you have multiple images of deforming object, how we come to know the NERF, right? The idea is that you have a canonical frame that defines both the color and density fields, right? In one canonical frame, then the observations is through all the frames, right? You want to know the NERF in a canonical frame, you need to have a mapping between each frame, which is actually 3D frame, and this canonical frame, right? This mapping is a 3D mapping, okay? Right? you have two frames. One is the original canonical frame, one is the deformed, right? You have many frames. You know two near fields in the canonical frame, right? If you want to know that, you need a mapping between the canonical frame and the deformed frame, right? Those near fields are defined in 3D, then this mapping, right? Those mappings are also defined in the 3D, right? Now, it's very important that this mapping is one-to-one, okay? If it's not one-to-one, what will happen, okay? A point maps to 2 points in the canonical frame, right? Then if you aggregate the colors, right, 2 points, right, you aggregate, right, you do some average, right, you aggregate. Then what will happen is that you have this blurry result, right? Because you do some average, right? So this means, right, this 3D mapping has to be injective, right? So this is what we want, okay? So how to enforce this to be one-to-one? So one strategy is you add some regularization, okay, to regularize the deformation field, right? The issue is that this is not strictly enforced. Then the regularization laws will compete with other losses, okay? Right? Later we'll have another problem that has similar issue. I will come back to that, okay? So what we want to do here is to have a way to construct the network, a network that defines this 3D mapping. And this injectivity is enforced by construction. And also we want this 3D mapping to be expressive, okay? Enough, okay? Right. So how to do that? The idea here is to compose injective 2D mesh deformations, okay? 3D injective mappings, very complicated topic, right? I think many people have worked on this. There are some ways to do that, not easy ways, okay? It's still open challenge, right? How to build a learnable approach to enforce a 3D mapping is one-to-one, right? But in the 2D domain, we have this beautiful idea, right? This is called turtle embedding. How many of you know this? Right, I think very good, right? You are from the geometry processing community, right? I think during the past SGP editions, we have sessions on this, right? So this is called mesh Laplacian, graph Laplacian, right? Right. So idea, right? So this is used in mesh parameterization, okay? And this is the reason why I like this, okay? Because, right, this comes from the geometry processing community, and it's relevant in NERF, right, which is the hottest topic in graphics right now. Okay, so what is a turtle embedding, right? You have a convex domain, okay? You fix the boundary, okay? The boundary has to be convex. You fix the boundary, right? So essentially what you can do, you can fix the boundary, you solve a Laplacian, right? To determine locations of the interior vertices, okay? Right? So you can, essentially here you can move the vertices around the boundaries, okay? Right? So the theory is that if the boundary is convex and we don't have flipping on the boundary, right? If you solve the graph Laplacian, then you get a mesh, right? Because you know the vertices, locations of the interior vertices. then this mesh has no self-intersection, right? This is a beautiful mathematical result, which is well known, right? How many of you know this? Very good, right? Very good, right? Okay, right? If we have this, then we have a way to define a 2D mapping that is one-to-one, right? So we can use bicentric coordinates, right, to define to interpolate this into a continuous 2D mapping, right? We can locate the point in a triangle, we get bicentric coordinates, then we can find its location in the target 2D mesh, right? Then you can actually develop neural network to define locations of the boundary vertices of a regular grid, right? Right? You can use MLP, right, ReLU layer, to enforce that the boundary vertices have no flipping, right? Just use a ReLU, right, which always outputs a negative value, okay? You can change the boundary vertices, you can have different meshes. You can have two different 2D injective mapping, okay? Right? So this is enforced by construction. Now, this comes from to the very simple, beautiful idea, okay? We need 3D mappings, right? How do you do that? Number one, a neural network has multiple layers, right? Nobody told me we can only use one layer, right? You can use multiple layers, right? How to extend this idea? Idea is actually very simple, right? So in each layer, number one, we can have multiple layers, okay? In each layer, we fix one axis, and we deform the other two axes, right? Then this becomes a lifted 3D mapping, but the underlying deformation is a 2D, right? Because we fix one axis. Then the deformation is actually 2D deformation, right? And we can construct the 2D deformation to be injective. Then the resulting lifted 3D deformation is also injective, right? One-to-one, right? And we can alternate fixing Z, X, and Y. We can have as many layers as we like, right? Each layer is one-to-one. We compose them, it's also one-to-one, right? The learnable parameters are essentially those parameters that determine the boundary vertices of the square in each layer, right? They're very expressive, right? So that is the idea, okay? Very simple idea, right? I do think this is beautiful, right? The idea comes from this geometry processing community, the mesh parameterization, okay? Right, so in practice, we use 20 layers. We alternate between Z, X, and Y, right? Nerve is optimized for each scene, right? So this is also applied for one instance, okay? So if we compose multiple layers, we can get very expressive 2D mapping, okay? Right, so this is the result, okay? Right, comparison, okay? The difference between an injective mapping and a non-injective mapping, okay? And we can also apply this idea to form a mesh model, right? For example, if you're familiar with simple model, if you change the pose and shape codes, right? If you change the pose code, you will not get a mesh that is self-intersection free, right? It's very complicated. But if you apply our machinery, right, which optimizes 3D injective mapping, we can get a self-intersection-free default mesh. Of course, you will have to add a deformation loss on top of that, okay? Okay, so that is the end of the first part. Let's have a 3 minutes break, then we will go to the second part. So we have 3 sessions, okay? Okay, let's begin. Okay, in the second session, I will talk about regression losses, okay? And I should say that this is something more general, right? And likely we can have some more frameworks, okay? I will share 2 views. One is very geometry processing oriented, two views, okay? The other is slightly less, okay, but also interesting, okay? The first view, right? So what is a generative model, right? Generative model, if you think about from the perspective of mathematics, right? So a generative model has a latent space, Z, right? And then you have a network. It outputs some instance in ambient space, right? So this is called, in the mathematical form, called a submanifold, parameterized by the latent code. This view was introduced in this CAPR workshop paper, okay? In fact, in the generative modeling community, few people know this paper, okay? Quite sad, right? Because I think this is a very important concept. The reason is that the image space does not have very good manifold structure because it's disconnected. You have many object categories. Right? If you go from one category into another, you have this discontinuity. But for deformable object shape spaces, we have smooth manifold, right? For example, the shape space of human bodies, animals, we have this nice manifold structure, okay? So I do have a series of papers on this. I will talk about APREC in detail, and chain analysis is a very latest SQL paper this year, right? And this methodology is also applicable to man-made shapes, right? The argument here is that you can say, oh, man-made shapes, we have this topological changes. But really, the notion is that this machinery only cares about the shape space locally, right? Because if you want to define a metric, you only care about the shape space locally, right? Differential, right? Geometry, right? Local geometry, right? So you can define this some many metric for unmade shapes locally, right? Even globally, you have some topological changes, okay? So what I will talk about here, right, are based on local quantities, right, of a generative model, okay? Right. Let's start with the first paper, okay? AIPREC, this is like less than 4 years ago, right, ICCP. Okay, so the goal here is to train a generative model defined by a graph neural network, right? So we have the latent space, and we decode the latent code into a mesh using a graph neural network, right? Mesh is a specific graph. I will not talk about the network architecture. That's interesting, okay? So we have a latent code. The output is a mesh. We change Z, we get the same mesh topology, but different mesh vertex locations, right? So we have many papers on how to develop such neural network architecture, right? 3D comma mesh curve. Each of these has like hundreds of citations widely used. Okay, a standard strategy to train those generative model is to use like standard distribution alignment, like GAN, VAE, auto-decoded those training paradigms. After training, what you can do is that you have two shapes, you find their latent codes, then you interpolate the latent codes in the latent space. Then you can decode the interpolated latent code into your interpolation, right? Because you have trained architecture that maps any latent code into a mesh. The problem is that the training objective doesn't understand the underlying deformation, right? So for those deformed shapes, you have some skeleton, right? You have some underlying articulate deformation. If you do not model those deformations, then the interpolations do not preserve those deformation structures, okay? So that is what we want to fix, okay? Now, how to fix this, right? So the idea here is to introduce some regression losses, right? So we can generalize the idea called active contours. How many of you know this? Well, some of you, right? So what is actually contours? Active contours, right? So you have a one-dimensional curve, right? You want to fit this curve to some image object boundaries, right? So how to do that, right? So you have two terms, right? One is a data term that aligns the curve with edges of an image, right? Then you have some regression term, right? You want this curve to be smooth, right? This is widely used, right? So intuitively, you can think about generative models as a generalizations of active contours, right? In active contours, S is one dimension. In generative model, it's like 100, like 72 for simple models, right? It's a high dimensional generalization, right? So the training shapes define the data terms. What is missing here is the so-called regression term, right? That controls the smoothness of the generative model. Of course, here we want better priors, right? Rather than smoothness, right? So this is what we want, okay? So the idea here is that given two adjacent synthetic shapes, right? We want to minimize some deformation between them, right? Intuitively speaking, this is analogous to minimizing the curve length in the active contour model, right? Here we generalize to minimize the deformation between two adjacent shapes. In active contours, minimize the distance between two adjacent vertices, okay? Right, so how to do that? We need a deformation prior, right? If we have a mesh, two adjacent meshes, the same mesh topology, a standard way to measure the deformation between them is called ARAP, right? Locally, it's a rigid transformation, right? This was introduced in SGP, right? I think well-known paper, okay? I'm not going to talk about that in detail, okay? Okay, so the nice thing about this is that number one, right? If we minimize this locally, right, we can still have very big deformations between shapes that are very far from each other, right? So it's a smoothness regression, right? We are not enforcing two shapes, right, to have minimal ARAP deformation, right? That would compete against fitting the generative model to training data. In fact, many of the 3D vision people, they actually just do that, right? I think it's not ideal, okay? Right. So here, this will not compete against fitting the generative model to the training data, right? Because this is enforced locally. Number two is that in the original ARAP formulation, you have this you have to solve a nonlinear objective optimization problem. We don't have a closed form solution. But if you only care about doing so locally, you can actually linearize the rotation, right? This was done in one paper in my thesis, okay? I did this in a U-graphics paper, right? Of course, at that time, I did not realize this is applicable for training generative models. Now, I think this probably is the best, most paper, the paper I really like for my thesis, okay? Okay, the idea here is that you can linearize the rotation, right? Because locally, rotation is close to identity matrix, okay? If we do that, we have a closed form expression, right? You have a quadratic energy, okay? In that paper, I used this quadratic form to do shape segmentation, okay? So in our case, what we can do here is that in a batch, we have half of the training shapes, and we have half of the synthetic shapes. Then for those shapes, we enforce a deformation, right? Defined in this way, right? J is a Jacobian matrix. HR matrix is a sports matrix induced from the AROP deformation energy. Okay, so you can minimize this. Very simple, very easy to optimize. And okay, we got state-of-the-art result. I do want to mention this table. Okay, so we actually tried this regression loss on top of 3 very different new architectures. Okay, so this regression loss is effective. Okay, it's very interesting that comma we get the best result on comma, right? Which is the worst performing architecture without regression, right? So the argument here is that it's better to learn the deformation from data, right? Because if you enforce the underlying structure, right, post structures in the architecture, right, because articulate deformation is not strict, right? If we enforce that through network design, it's less optimal. In fact, mesh curve COM, right, is an approach that really defines the deconvolution networks so that the layers align with the underlying post structures of human body model. Okay, that achieves the best result without regression, but then it's too strict, so it doesn't offer the best result. Okay. Okay, I want to briefly mention this paper. Okay, this is Sigma paper, Asia paper, 2 years ago. So what we did, we used this paper, right? In fact, this HR bar matrix is a Riemannian metric. It's a D by D matrix. This is a dimension of the sum manifold. D by D matrix, which is a semi-positive definite matrix, right? This is a pseudo Riemannian metric, okay? Right? It's a pullback metric of extrinsic deformation energy, right? J is a Jacobian, right? We have a Riemannian metric, right, of this sum manifold, right? If you have a Riemannian metric of a shape space, right? So what people do, right? So this is a well-known paper, right, called Geometry Modeling in Shape Spaces. In fact, if you read any shape space paper in differential geometry in the shape space community, they all have one application: how to compute the geodesic interpolation between two shapes, right? The geodesic interpolations will give you the most pleasing and the least distortion interpolation, right? Now, if we have this generative model, the ideal way to define the interpolation is through linear interpolation, right? Interpolate the latent codes. But then this is not a geodesic interpolation, right? Now, if you really want a geodesic interpolation, you need to solve a PDE, right? Which, of course, is much better, right? Because you don't have this shrinking arm, right? But then it's complicated, right? You have to solve a PDE, right? Now, the question here is that, can we actually enforce all the linear interpolations of geodesic curves? Can we do that? The answer is that no, right? Or then the metric has to be constants. And this means the shape space is zero curvature, right? Which is a Euclidean space, right? Then, if we only enforce that all the interpolations within those two-dimensional subspaces are geodesics, right? Then this is also too strong, right? Because you apply this without, this is also a Euclidean space, right? Two-dimensional subspaces are also strong, too strong. Then the idea is to enforce that we have axis-aligned geodesic interpolations, right? And this is a generalization of the so-called geodesic web, right? So you use geodesic curves, right, to cover a shape, right, which have applications, right, in architecture, right? So this is a generalization of a geodesic web, right? And we show that you can enforce this locally, right, by enforcing another objective laws, right, some visual result, right? So this is the desired geodesic interpolation. This is without regularization and linear interpolation. This is adding regularization during linear interpolation, right? It's becoming close to geodesic interpolation, right? Right. So this is another result. Okay. Okay. And some user study. And nice thing about this is that if the axis are geodesic interpolations, then it becomes natural to enforce this pose and shape disentanglement, right? Along each axis, you have this pose variations, and this variations is along a geodesic path, right? So this is a desired property, okay? Shape variation. Okay, I want to spend like 5 minutes talking about a generalization this, okay? The two previous papers are based on learning mesh genetic models, okay? If you're trying to learn a mesh genetic model, you have to have consistent meshes to learn the genetic model, okay? This becomes very strict, right? In practice, right, if you scan shapes using 3D scanners, you don't have correspondences. Now the question here is that, can we actually learn genetic models without correspondences? Yes, you can, right? So this is called implicit representation, right? Deep SDF, right? You just have a loss that measures the distance between points and the underlying implicit representation. And people actually extended this to deforming shapes, right? This 1 year after, 2 years after deep SDF. So what they actually realized, right? You can see, we do have shape variations, but then all those shapes have similar poses. So I can tell you that if you have large pose variations, if you don't do this naively, it doesn't work, right? That's the reason why they did not show, right, examples with pose variations. Very similar fact is that you train genetic models of chairs, right? You have to have consistently oriented chair models. Otherwise, it doesn't generalize. Okay? So our idea here is very simple, right? We fix the architecture, we fix the data loss, we add 2 regularization losses so that now we can have pose variations, So that is the idea, okay? Now, what we really want to have, really to define the regularization losses, is to solve the so-called correspondence problem, right? Because if we can parameterize the genetic model locally, like if we have an implicit surface, we discretize the surface into a mesh, then we know the correspondences of the mesh vertices on the adjacent implicit surfaces. Then essentially we have a mesh generator, right? Then we can define the regularization losses, right? Similar to AIP reg, right? Then we are done, right? So that is the idea, right? So what we really need to do is to convert the implicit shape, right, into a explicit generated locally by solving a correspondence problem, right? So what is the problem, right? We have two implicit surfaces. If we have points on one implicit surface, we want to find their correspondences on the adjacent implicit surface, right? So this problem, right, people have studied in the level set community. The widely used strategy is to displace the point in a normal direction, right? The challenge here is that you have one constraint, you have 3 degrees of freedom, right? The correspondences can float on the surface. If you shoot in the normal direction, you have a unique solution. But the problem here is that you don't, then if you do this, you have a sphere on the translation, you don't recover the translation, right? That is the challenge. So how to address this issue, right? The idea here is to solve a constraint optimization problem, right? We have the implicit constraint, right? The constraint specifies that the correspondences lie on the adjacent implicit surfaces. Then we also want to minimize some deformation energy, right? If the underlying translation is a ridge transformation, then the loss is 0 if we cover the ridge transformation, right? Then we address that issue, right? And if we do this, we have a closed form expression, right? You only need to prefactorize a sparse matrix, okay? Because this L bar matrix is sparse matrix, okay? Right? You can prefactorize, okay? Now, if you have the correspondences, the rest becomes easy, right? You can define the deformation energy, and you can add another regularization loss among 3 adjacent shapes, right? So that the correspondences are cycle-consistent. And this actually corresponds to the curvature regularization in active counting models, right? G involves the gradient of the object genetic model, okay? And the gradient of G is second order derivatives, okay? Okay, so this is the interpolation without regularization, right? Right, this is the difference, okay? Right? Okay. Right, you can really see the difference, okay? So this year, we extend this idea to memory shapes, right? As I mentioned, you only need a mesh parameterization locally, right? So what you really need to have is to change deformation energy so that it's applicable to memory shapes. So here we defined as as possible deformation energy, okay? A nice thing about this is that the interpolations, it actually preserve part structures, okay? Then once we have trained this genetic model, we can use this genetic model to do tangent space analysis, right? So what are the shape variations, right? If we enforce as far as possible, right? Those variations have piecewise affine structures, and we can extract segmentation cues by doing this tangent space analysis, right? Those are local analysis. We can also use interpolations to derive intershape correspondences, right? Then we combine those segmentation cues and intershape correspondences, and we can do co-shape segmentation, okay? Okay, then we can get state-of-the-art result, okay? Okay, all right. Let me briefly talk about another view, right? This is called, if we have a shape generative model, then we can define the so-called quality checker, okay, of a shape generative model, right? We can evaluate a generative model, okay? This is less relevant to the geometry processing, but certainly related to physics, okay? But I really want to convey the idea, okay? Hopefully many of you can really understand the idea, okay? Right, so let us take another maybe 2 minutes because I'm running out of time, okay? Like 2 minutes, okay? Okay, let's get started, okay? Because we are running out of time. Okay, let me be quick, okay? I will skip some of the mathematics behind this, but I really want to convey the idea, okay? So this is a CVPR oral paper last year. I want to briefly introduce the idea, okay? So the idea is to use diffusion models to train a generative model, okay? This is widely used in the 3D vision community, right? Diffusion models, when they came out, in the 3D community, people did not follow immediately because we don't know how to define the so-called Gaussian distribution of implicit shape, which has infinite dimension, right? We know how to define like a Gaussian distribution of point cloud. But 3 years ago, latent diffusion came out, which combines representation dependent decoder and representation independent latent diffusion procedure, okay? So the decoder can be implicit, can be mesh, can be monometric. Then in the 3D community, people were very happy, has been very happy, okay? Whoa, we can train a implicit decoder, right? We have latent code, we decode into an implicit shape, right? Then in the latent space, we can train a diffusion model that maps Gaussian distribution to the distribution of latent codes of the training shapes. About 500 papers in the 3D community, right? They follow latent diffusion, okay? Of course, there are other reasons, okay, for efficiency. This is appealing, right? Because now, right, if we run 3D shaped rect set, I think this representation is still widely used, okay? We have some issues like geometry, physical issues, right? Artifacts. This is easy to understand, right? Because if you train a latent diffusion model, right, you still use latent codes of training shapes, okay? Now, if you have a pre-trained decoder, okay, so this is the most important idea of the third part, okay? I hope all of you can understand, and this is very easy to understand. If you have a decoder, okay, pre-trained, that is fixed. For any latent code, you can get a corresponding 3D shape, right? Then you can evaluate whether this shape is good or not. How to evaluate? If the shape is disconnected, has multiple connected components, right? Which is, you can evaluate, right? If it's disconnected, then you know this latent code is bad, right? Then when training the latent diffusion procedure, right, we should not sample the neighborhood of this latent code, right? You can generalize this idea, right? You can evaluate, assess whether this shape is physically stable or not, whether if humans can easily interact with the shape. You can define anything, right? Everything. So you can generalize this idea to a quality checker, right? Which is a continuous function of any latent code. So essentially the training shapes, their latent codes are discrete, very sparse. But this quality checker is a continuous function, right? So I do think for 3D generation, if we use latent diffusion paradigm, we can actually define this quality checker, right? Then we incorporate this quality checker into learning the diffusion model, right? So I think this is a very powerful idea. And this is very 3D specific, right? So that is third view, okay? I think all of you should understand, okay? Now, you may say that, oh, this is relevant to classify guidance or classify free diffusion, right? Which are widely used in image generative models, right? Right. There are two distinctions, right? Number one, this is used in the sampling procedure, right? You are not improving the noise network, right? You just avoid sampling those shapes during the sampling procedure, right? Then if you do that, you have the trade-off between diversity and quality. Number two, you need the gradients of the classifier, right? So what we want here is we don't need gradient, right? Because the shape is connected or not, it's a binary, no gradient, right? And we want to improve the noise network, right? The training, okay? Okay, I'm going to skip this, okay? So the idea here is that what we do is very similar to ARP-RAG. In a batch, we have some of the latent codes of training shapes. We also have latent codes that pass the quality check. They are good latent codes, right? Then we have latent codes of training instances. We have latent codes of those good ones, good latent codes, okay? Then we have half training shapes, half some of the latent codes, okay? And then we did some theory how to find the trade-off parameters between those two data sources, okay? We did some math. Because one is discrete, another is continuous, right? So we need to balance them on the different noise scales. By the way, for this training loss, right, this is widely used in training diffusion models. For the interest of time, I'm going to skip this, okay? Okay, I'm also going to skip this. How to define the quality checker, we actually did this structural analysis, okay, worst case structural analysis, to quantify a shape is physically stable or not, right? We also learned a neural network to quantify the geometric fidelity, right? Because you have bad geometry but physically stable shapes, right? So this is dirty part, but I think the idea of training a linear quality checker is very important, okay? Okay, let me skip this. I want to mention that there's certain limitations, right? If you train a latent diffusion model, we fix the decoder, right? If the decoder is not optimal, then we have to know a very complicated distribution in the latent space. And this is very difficult to learn, okay? Okay, so very recently, we also applied this idea for CAD models. Okay, CAD model is defined by a sequence, right? If you learn a generative model to synthesize a code, you can also check whether the code offers a valid CAD model or not, right? Also using a quality checker. Okay. Okay. Let me spend 5 minutes on this part. It's about topology, right? 5 minutes, okay, bear me. So some of the issues are also topology issues, like host, disconnect component, right? So I do think that topology is complementary to geometry, right? Geometry is the local quantity, right? Topology is global, right? You can have many physically stable shapes. You have a lot of small holes, but they are physically stable, but they are not really topologically feasible, right? Right. So how do you enforce topology, quantify topology, right? So we have the notion called the Poisson diagrams, right? How many of you know this? Okay. Right. I gave talks in many universities, right? Nobody actually know this, right? Quite sad, okay? It's good, right? I think we do see many papers on this at SGP, right? So what is a Poisson diagram? We need a filtration, right? Poisson diagram, if we have filtration, Poisson diagram is a 2D point cloud where the coordinates are local minimum, local maximums of the filtrations, okay? Right, so we have a mapping, okay? So if we have a implicit shape generator, right? We have 3 Poisson diagrams that correspond to number of connected component, number of loops, number of voids, right? They're also sparse point clouds, right? They all map to local minimum, local maximums of an implicit function that defines the implicit shape, right? And we also have 2 well-known papers, right? It's good to talk about this, right? Both papers are SGP papers, right? One a couple years ago, right? Another 5 years ago, right? So both co-authored by Max, my academic brother, right? So the idea here is that if we have a Poisson diagram, 2 minutes, okay. If we have a Poisson diagram, you can actually optimize the function so that the optimal function is Poisson diagram matrix, okay? Right. So now, so this is one paper. We did this to optimize an implicit function so that, right, if you optimize the implicit function so that we do not have topological changes of a deforming hand, right? So the idea here is that you add a loss between those 2 implicit fields, okay? Right? Okay. Okay, so this is another paper. If you want to apply this to a generative model, what we do here is to learn a point cloud generative model, okay? Point cloud generative model to generate Poisson diagrams of the training shapes, right? And they actually generalize a lot better than the implicit shapes come from a deep SDF, right? Now, what we do is that, right, they generalize all the better, right? So on the left, it also generalizes very well, right, in the topological sense. On the right, this is a point cloud generator of Poisson diagrams, right? They generalize a lot better, okay? If they generalize a lot better, the idea is that we learn PD point cloud generators, right? Then we enforce PDs of implicit shapes along with the PD generator, right? How to do that? Those come from the 2 SGP papers, okay? Right? So this is a very simple idea, right? We generate synthetic point cloud that correspond to persistent diagrams of the synthetic shapes. Then we have an implicit shape generator. Then we add loss between them using 2 SGP papers. Then we are done, okay? Very simple idea. Right. Okay. Right. And quantitatively, we get better result, and we have less topological artifacts. Right? Very simple idea, okay? Very simple idea, okay? Okay. Sorry for rushing this, but I hope that the main ideas has been conveyed, okay? So we want to say that 3D generative model is different from image generative models, right? And this is a field where machine learning and computer graphics techniques synchronize. Many problems to work on, right? I'm here for a couple of days. I'm very happy to talk to you if you are interested. And I want to acknowledge, right, funding agencies. I think they support this trip, right? They provide funding for travel, okay? And also industry funding, okay? Thank you.